Let's solve the following differential equation. So here, this is a homogeneous differential equation. And to check whether if it is homogeneous or not, we need to rewrite this differential equation as dy over dx. All we are doing is dividing both sides of this equation with x squared. So our first term will become x squared over x squared, so that's 1. Minus 2 times, so we have y squared over x squared. We can rewrite it as y over x whole squared plus xy divided by x squared, so this will become y over x. So this is our function which can be expressed as the function fx comma y. And now if we make a substitution meaning if we substitute the value of x with lambda x and the value of y with lambda y into this particular function, then we will get back our original function. And when this criterion is met, we can say that our function f of xy is a homogeneous function. Since the function is homogeneous, so our differential equation is going to be a homogeneous differential equation. Right. So that was the first step, to check its homogeneity. The next step would be to solving the differential equation. However, we cannot use the method of variable separation because here it's a function of f of x and y. In order to use the variable separable method, the function should be a product of two functions where one is a function purely of x only and the other is a function of y only. Meaning, if we could express f of xy as the product of two functions h of x and g of y, only then we can use the separable method. But in this case, in a homogeneous differential equation, we cannot do that. This can be achieved by making a substitution. Let y equals to vx, or you can say v will be equals to y over x, and we will differentiate both sides of y equals to vx with respect to x. Then this will give us derivative of y with respect to x equals to, apply the product rule, that will be b plus x times dv over dx. Now we will use this value v equals to y over x and the value for dy over dx and substitute into our original differential equation such that this differential equation now transforms to v plus x times dv over dx equals to 1 minus 2. So here we have y over x squared, so this will become v squared plus y over x, which is v. And immediately we can see that v and v cancels out, and we will have the differential equation x times dv over dx equals to 1 minus 2v squared. Or simply put, dv over dx equals to 1 over x, so we're dividing both sides with x, multiplied to 1 minus 2v squared. Now what we have product of two functions. One is a function of x alone and the other 1 minus 2v squared is a product of v alone. So this means we can use the method of variable separable now. We have dv divided by 1 minus 2v squared equals to dx over x. So this is in the variable separable form. Now we can integrate both sides. The integration on the right side is extremely easy. That's simply going to be natural log of x. Now we have to tackle the integral on the left hand side. What we can do, we can rewrite. Let's do it here. So we have integration of dv over 1 minus 2v squared. If we take 2 as the common factor in the denominator, then this will be half minus v squared. We can take out the half and multiply to integral dv. So we have 1 over 2, so that can be also written as 1 over square root of 2 whole squared minus v squared. So this will be now in the standard form, which is dx divided by a squared minus x squared. Now this has a formula. So this is given by, we already have the half. We'll replace the value of a and x with the value 1 over square root of 2 and v respectively a little bit later. First use the formula here. So this has the formula 1 over 2a times natural log of a plus x divided by a minus x plus c. We have the constant of integration. Let's call it c1. Now here a value is 1 over square root of 2. So this is, we have half multiplied to 1 over 2, so this is 4, and a value is 1 over square root of 2. Multiplied to natural log of, so we have a 1 over square root of 2 plus x. So here x corresponds to the variable v, divided by 1 over square root of 2 minus v plus the constant of integration c1. Now let's substitute it here. This is the integral value. So this will become square root of 2 divided by 4 times natural log of, so this will be 1 plus square root of 2 times v divided by 1 minus square root of 2 times v equals to the integration of dx over x. So that will be natural log of x plus the constant of integration. Now here constant of integration will be the contribution from both the two integrals, but we'll use one common constant. And since everything is written in terms of logarithm, so we'll consider that our constant of integration is also in the form of a logarithm. So let's call it natural log of c. Right. Now we will substitute the value of v with y over x. So this is square root of 2 over v times natural log of 1 plus square root of 2 times y over x divided by 1 minus square root of 2 times y over x, which is equals to natural log of. So here we can use the property of logarithm to combine the sum of two logarithms, which will be simply log of, this is absolute value of x times c. Fine. Now what we can do, we can take the square root of 2 over 4 to this side by multiplying each side of this equation with 4 over square root of 2. 4 over square root of 2. So that means we have natural log of, now here these two can be further simplified to x plus square root of 2 times y divided by x minus square root of 2 times y equals to, so 4 over square root of 2, so that will be equals to 2 times square root of 2 times natural log of x c. Furthermore, we can again use the property of logarithm to raise it to the power of xc. So that means this will become natural log of x times c whole raised to the power of 2 raised times square root of 2. And we already have the, now what we can do, we can get rid of the logarithm from both sides. So this will give us x plus square root of 2 root 2 times y divided by x minus square root of root 2 times y equals to x times c whole raised to the power of 2 root 2. So this is the final solution, or you can say the required solution to our given differential equation.